It's a pleasure to have Anne de Bouard here, who will give us a seminar about nonlinear Schrodinger equations. She probably will write down the title more precisely.
Okay.
Or say it, don't you need to write.
Okay, thank you very much. So something like stochastic. And modulation of solitary waves. So this is what I'm going to say today. The joint work with École. From Japan.
The red light on the mic.
Yes.
Is it a problem?
Yeah, she's in same line. So our aim with Rita is to study from a mathematical point of view a model equation which arises in those So Bose-Einstein condensation it consists in confining some specific atoms in such a dense and cold way that at least the macroscopic part of the atoms get in the same state of minimal energy, right? And so at the origin, because the first experiment in Bose-Einstein condensation was performed in 1995. So I think in the US, and the team who did that had actually a Nobel Prize for that. But it was predicted by Bose and Einstein in something like 1925. So that's why it's called. So Bose-Einstein condensation. So at the origin, the way people did to confine the atoms was by using magnetic fields to trap the atoms. And actually later, it was I think the first time was in 1998, some people finally managed to use an entirely optical confinement. That is, instead of using magnetic traps, they use lasers, all optical device. And so, according to the physicists who did this experimentation, this could have some advantages, like being able to get different geometrical form for the condensate that will less depend on the magnetic properties of the atom and so on. But on the other hand, if you use a laser to confine, then you may have some fluctuations in the laser intensity, and that could give some stochasticity in the model, and that gives the model that we want to study. So, at least for the case where you don't take into account the stochasticity in the density of the field, there is a kind of mean field theory which leads to the fact that the condensate is described by a macroscopic wave function. Of t and x, and this function satisfies nonlinear Schrodinger equation cubic one, which is usually called actually the Ross-Pikayevsky equation. is because these are the first two. This equation using the new future. So now, in the case where you take into account the stochasticity for the fluctuation, well, I mean for the intensity of the electric field, then there was a model which was proposed by some other people. Published in nonlinear. And so their model is written this way. So for this macroscopic wave function psi, they write that I dt psi would be minus. So it's written in it's a 2D model. And it's radially symmetric, so that R is just the radius. Explain all these terms after. So here, so as I said, R is just x squared.
X squared or X?
Oh, sorry, yes.
I'm just asking. No?
Yeah, no, you're right. So the function is supposed here to be radially symmetric. And chi here is a coefficient which is mainly because this has been renormalized so far. So we don't have it. So key, in this case, you can take key.
So chi is just a constant.
It's just a constant. It's mainly the sign which is important. So
Okay.
it's plus 1 or minus 1. And this is related to the fact that it's plus 1 or minus 1 is related to what is called the scattering length of the atom. So it's very specific related to that. So it's specific to the kind of condensate that you have. You may have attractive condensate. The case, so if chi equal so it's plus 1, you have what is called dissolving condensate. And chi equal chi. Because it changes a lot the behavior of
But it's equal to, you have really two equations, right? Is it chi equal 1 or chi equal minus 1, or does it change with R?
It's a parameter in the equation, but it changes a lot the situation. I mean, the.
Yeah, but you have two models, right?
Yes.
Yeah, it's not like R.
But it's, the model you have to use depends on the atoms that you are considering.
Okay. Thank you.
Gamma is damping coefficient, so gamma is positive or can be 0. It's actually takes into account the interaction between the condensate itself and the atoms which are not condensed. So the effect of the atoms which are not condensed is a damping effect on the condensate. So if you have non-condensed atoms, then you can decrease the number of atoms in the condensate. So this is the effect of this. This is the influence. But it can be 0 if you consider that all the atoms are all the atoms are in the common scale. And finally, this coefficient E of t is the fluctuation of the electric field intensity, so it's something like the E of t minus where E of t is the electric field intensity. And not and in the model, they assume, well, in particular in their paper, assume that E of t is just a real valued Gaussian delta correlated process.
So for E0, we just have classical harmonic oscillator. Some sound. Not the linear part.
Yes, what you have, what is called usually Polytechnique, well, it depends on the process. Some people call it Polytechnique, something which is a little bit different. It's typically a nonlinear Schrodinger equation with this harmonic. Okay, so this is the model which we wanted to study, and I will explain why it's a little bit different than the so we a little bit generalize the equation in the sense that we consider this one. As usual, we will take more general power term. So delta sine t was this term, but we put here a power 2 alpha. So alpha may be something different than 1. The reason for that is always the same, is that there is some critical effect of this power alpha, which is related to the dimension of the space. So we want just to be able to compare this critical. And we can have this damping term or not. I will say when at some point we will have to drop it out, but I will explain that. Okay, plus the noise, of course. And the noise will be of this type. So I put an epsilon because at some point we will have a small noise, and which is rather natural because of course this is small issues. And so here we put a Stratovich product, right? And W of t is just standard. So why Stratovich product? This is, for me, it's natural. As I said, in my opinion, most of the physical model, when you put noise, at least when they arise this way, in this kind of equation, at least. And the reason is, so first, because of course this is a limiting case on at the origin, the fluctuations are just processes with small correlation length, not really zero correlation length. And the second reason is, so this is the reason and also because this is the only way that we have to preserve the total number of atoms in the case where we have no damping. I didn't say that here we take also general dimensionality, but mainly we will be restricted to a 6 dimension. Even less than, yes. I will explain. So this is this total number of atoms which should be preserved if there is no damping. Of course, if there is the damping term, then this is no. So, as I said before, there is something which should be noticed here. So, of course, we can rewrite this equation in equal form. So, how is the correction if you write it like this? So there is a Ito correction which is of the form minus. And
did you say anything about the? I missed something. The linear noise. Is there a physical meaning for that, or?
yes, because it's just fluctuation here. It's fluctuation.
What do you put a
the
perturbation
trapping
in the middle there?
Yeah.
Okay, a random perturbation.
Yes.
Okay. Thank you.
Okay, so this is the equation. In Ito form. So why is it a little bit different than before? We had studied with we had studied an equation of the form IDU, same kind of nonlinear term. Plus a noise which wasn't so linear of this type, and it would also depend on the space. So, as usual, when you treat this kind of equation, actually what we did was considering that this is a perturbation of the all these terms are perturbations of the linear equation. So that we wrote the solution as less like this, and we estimated these two terms by using the properties of the group. So U of t that is the solution. U, it's just, I mean, U of t is just e to the I t. So here the trouble is that if you do that with replacing e to the it delta by the exponential of this, t times this operator here, you can do, this generates a group. This is a self-adjoint operator on L2 with a well-defined domain. Slightly. There is no trouble except that when you try to, so I guess you won't see anything if I write here. Except that if write what is the L2 norm. So I did not by you so the thing which would correspond to this option here is differential of L2. So this means multiplication by x squared. So if you try to compute the L2 norm, the expectation of the norm like this would be, of course, and because this is conservative, this preserves the L2 norm, which will be so it means that estimating this terminal 2 would price like this. So this is not a perturbation of the, from that point of view. So what we had to do, so the main topic of the talk is not the existence result. We studied the problem in the which is we actually used the complete linear equation with the noise. Just solve.
So somehow you would need psi to be in the domain of your operator, yeah? In what you wrote above.
No, well, I don't want really such regular solutions.
Okay.
We have
Weak solution.
typically the domain 1/2.
Mm-hmm.
I will.
Okay.
I would say this. Well, okay. I didn't say that, but it's important. What we are really interested in are solutions which have finite energy. So what is the energy here? So energy for me is not L2 norm, is the Hamiltonian. Because, so you can see that actually this, when gamma equals 0 and there is no noise, then the system is actually an Hamiltonian system of the form psi by t equals j h prime of psi, where j to write it like this, you have to identify, of course, this is a context valued function, you have to identify it with a r squared valued function, because otherwise your Hamiltonian will not be differentiable. And so this is just a multiplication by I in this situation. And h is the Hamiltonian, which is 1/2 of the gradient psi squared plus k over 2 alpha plus t, the integral of psi. This is the, and this is of course the first derivative when you consider that psi is a function with values equal to x, right? So because we want, for lecture purpose, to use this Hamiltonian, we need to have solutions which are such that this is finite on the path of the solution.
Excuse me, now you once more talking about the non-linear equation, not about the linear one alone.
Yeah,
Sorry?
because
Yeah, no, what I've written, because
Because this is the Hamiltonian for the non-linear equation.
yes. It is not the, I mean, it's I should have said that before going to the linear equation. But this is, okay, so we're interested in finite energy solutions. So we, as I said, we first solve this random linear equation. So we have a random propagator. So this can be done. I mean, it's not difficult. And this photo is already books in which you have theorems which solve that directly. And then you have a random propagator. You need to solve the linear equation. And we get a random propagator, which is nothing else than u omega ts, right? Psi equal I psi. Psi minus x squared. Psi, I x squared. Oui, va chercher S. And then we apply this dimensional constant formula or whatever you want to the nonlinear equation. That is, you solve finally this the equation u of t equals u omega t s plus plus the integral your nonlinear term. Yes, no more stochastic. So the trouble we had in doing that, and this is why our result is up to now resolved, but we are working to improve it. So the trouble we had is that we don't have good estimates on this that are able to treat the nonlinear term in high dimension. So for that reason, we are restricted either to dimension 1. Dimension 1, of course, there is no problem because the space. So I didn't say what the energy space was, but the energy space is obviously the space. Oh, sorry. There is a mistake here. The x squared term should appear.
Yes, yes.
Yeah,
Well, it was clear. Mm-hmm.
okay. You should have told me. I don't really realize what I write on the board. There is this term also.
Otherwise, you would simply land on Fujita constant in the exponent, that it would be not so interesting. What is the alpha then? What is the critical alpha?
So the critical alpha is, there are two critical alpha, actually.
Yeah, tau and tau.
So in dimension 1, you can solve the locally equivalent for any positive alpha. And d equal to, and alpha is less than or equal to 1. So this is not this is less than the critical deterministic alpha, and this is due to the fact that we don't have good estimates on this. So these are the cases where we are able to solve from C0 in what I call sigma. Sigma is the energy space. That is H1. H1 space, H12 if you want.
Yeah, but with the
You'd rather
x
take
squared.
the energy
squared.
space. Oh, yeah.
XU. This is meaning the energy is finite, as long as this is true and alpha is not too large compared to the dimension. The critical case where locally nonlinear problem. In this case, there is a local solution, so that there is a stopping time to start, and a unique solution time, which is almost truly so. I mean,
It's a local solution, yes.
it's a local solution, and moreover, actually, it's not. So if d equal 1, then you get continuous path with values in sigma, and if d equal 2, the continuity is only weak. That means mainly you have the Fed infinity because we use a compactness method. That's what we have to do.
What is the reason for the explosion? Is it the nonlinear term?
Yes.
U is the 2 alpha.
Yes. So moreover, if
But if alpha is less than a half,
sorry, I didn't.
I said if alpha is less than a half,
Switch it off.
Alpha is less than what?
I said if alpha is less than or equal to 1/2, then you probably should not get any explosion. Is that right?
Yes. Well,
Is that correct or no?
what? Not what. In dimension 1, it's alpha equal 2, which is the critical case. So alpha equal 2 also if you have some additional condition of equal to. In dimension 2, the critical case is alpha equal 1. Okay, so alpha less than 1 or so alpha equal 1 you can accept or alpha equal 2 also. But in this case, the initial state has to be less than some fixed constant. So this is done with the use of this Hamiltonian term here.
I'm also wondering about, sorry to interrupt you, the random propagator.
Well,
Because it was written information that it's even there. That the mobile phones could
no, this is
interfere.
not because of this. Well, laptop gives not the less magnetic field.
I don't know, I'm just.
No, it is usually when microphone is too close to the loudspeaker itself. I think you can switch it off. We are not too many in the.
As a recorder.
That is recorded.
Ah, there is a recorder. Try to fix microphone higher.
Hello? It's noise.
Yes. Is it every time you speak?
I think also somebody
Other-
in front also. I don't know. You know?
No.
He doesn't seem to know why.
So,
Yes, you can ignore it.
There exists blow up.
There exists a lot. There are psi nodes for which with positive probability. Okay, and moreover, because that will be useful, if I start instead of, so here I only have a weak continuity in time, but if I start with a more regular psi naught, actually I have solutions with solution which is continuous, we are using sigma and weakly continuous, like using more regular space, but on the same time. Always exists. It's what I call propagation of regularity. With this notation object is the domain of the operator. Okay, so just a comment on.
Just can I ask a question here? Because you say with some tau star, is it not the same tau star there? So when you say propagation of regularity, do you mean that if I have a solution, maximum local solution, and if this maximum, and if the initial data of maximum local solution is in sigma 2, then it stays
In sigma 2, as long as it is in sigma, exactly.
okay?
But is it? It's not getting any better this time. Is that has any smoothing effect?
There is no.
No smoothing. So is it a homeomorphism? Or what do you think? Even in the case when tau star is infinite.
Yes.
You know, the nice case is d equal 1 and d equals 2 up there.
Mm-hmm.
Do you have a, what is it, a Fredholm? You have a cocycle that maps, you know, the space into itself?
You mean for. You mean it?
I think there is cocycle because it's one-dimensional Brownian motion.
Understand?
Well, okay. I don't know if I understand very well what you would like to have.
But
If it is like a continuity with respect to the path of the Brownian motion, we don't have this yet. Because here we only have the solutions using compactness method. But I have some hope that this is true. But this was the comment I wanted to make right now, is that we had to use, as I said, our result is quite weak because here we restricted to the case alpha less than 1. That is because we don't have the right estimates, like strict odds estimate.
But can you write them down exactly what sort of estimate do you want?
Yes. So the estimate we would like to have is dispersivity. That would be something like taking so you have a time variable and a space variable, right? So no, first the estimate you would like to have would be like this one. First, it's only a space variable estimate. It would be like this in LP square, LP of RD less than a constant time a negative power of time, T minus S. And the initial condition in the conjugate. Because this is true for the deterministic equation, both with the harmonic or without the harmonic potential. Actually, there is a transformation which transforms the group corresponding to the equation without the harmonic potential in the the linear potential.
But for harmonic, you cannot have it for every T and S.
No, this depends actually on say for. But this is sufficient because
But for small T and S.
this is sufficient for our purpose. This would be sufficient. So we are.
Sorry, so you mean a pathwise? You mean omega by omega estimate? Or what do you?
Okay, this is not clear, but we can have up to now. No,
Pathwise
not
is only
necessarily.
reversed.
I mean,
What's that subscript there?
no, you're right. Here you have omega, so you should have something in the. Okay, like for example, like this. Something like this. But I strongly believe, as you, that the solutions are indeed continuous with respect to the path of the Brownian motion, and but the details are not completely fixed. But I believe that actually we can have some kind of estimate with a constant that depends on omega but for fixed. I believe in that, but this is not completely.
But it's not continuous in U0, or is it? On the initial condition.
In which space?
Well,
Yes.
whatever space you have such choices, a lot of choices, isn't it? You have H1.
You mean what is
you have-
continuous? The solution here?
Mhm.
Um,
Or even the.
but this one we have in dimension 1 there is no problem. You have the continuity with respect to what you completely get the solution by
So you have
by
the
a contraction principle. So there is
Oh,
no
okay.
trouble here.
omega
in
wise.
dimension 2 we
Omega
have
wise.
to use.
Correct? For each omega, for one set of omega. It's pathwise.
No.
It's not? Because you have a random equation.
Um,
So you are very close to that.
yeah. Yeah, I believe it's that's why continuous.
Seems likely, but I don't know it as well as you do.
In dimension 2, it's not, for sure, because the method is a compactness method, so I don't believe we have it. Except if we can get this kind of estimate, which I believe we should. So now it's not a question of this.
Parabolic, you would have it for sure.
Yeah, sure, but it's not parabolic. I mean, it's very, very different. I have to keep that in mind.
Do you have a Feynman-Katz formula for this?
Which one? For the
linear
that's the
equation.
question. In some well, that to my knowledge, there is none. I asked, for example, Alpeverio about such things, and he was at that time he told me that with they have something with an x, a potential like x, Stratonovich, right?
It doesn't matter if it's Stratonovich or
Okay, but I mean the potential itself, instead of the x squared, if it's x, then okay, but x squared, they can't. If I understand very well what you are asking for, I think that up to now there is no really result with this kind of potential. So the way we do to try to get these estimates is using Feynman path integral, but from a more deterministic point of view, using stationary space. So we have very good hope to have a kind of representation of the fundamental solutions in terms of Feynman path integrals.
I find it difficult to believe that you don't have a Feynman-Katz formula for this, for the linear equation.
With you mean the linear equation with the noise? With the noise.
With the noise.
With the noise. I couldn't find anything on that. I don't know.
Well, the one thing is
if-
whether it
okay.
is true, another thing
So
whether it is not.
if you didn't have the noise, do Do you have a Feynman-Katz equation? A Feynman-Katz formula?
Yes.
Yes, without noise, yes, sure.
Right. So then, what is the difference?
Maybe that's a topic
There's
for
no
another
difference.
talk.
Well,
We can discuss later.
well, we will discuss later because I'm not sure I see very well what you.
Yeah, okay. I think we need to move on.
Yeah. So what actually I wanted to talk about was the fact that the deterministic equation deterministic equation. So from now on, I take gamma equals 0 and I is supposed to be -1, that is, I have attracted point. So in case there is no noise, we have a two-parameter family of solutions. Which is of this form, e to the I theta plus mu t times some t mu, which depends also on x, only on x. So there is of course restriction, so theta can be anything. This is just due to the Gaussian variance. And mu has to be here larger than minus the infimum of where you restrict u to be over 2 equals to 1. That is the first eigenvalue of the 0 minus delta plus x squared. So what we wanted to do, so if you try to analyze what is the deterministic behavior of what is the behavior of a solution close to this kind of solution. And the first thing you can do is linearize the equation. So you write, this is still deterministic. So write your solution u so in the frame of this stationary annual solution. So we have one term here. And what is the structure of the linearized equation for V? Then it's like dV by dt equals J and mu of V. Again, we see the symplectic structure that we have. So to linearize, again, we have to assume that V is some domain of R2. And so J is still this multiplication by I, and then mu is an operator which has the form which is here. So the two operators here are close, but not totally close. And it makes that the two J and then mu do not commute because of the presence. So this is.
So in the second one, there is no coefficient alpha.
Yeah, that's the difference. another way of saying this is that the phi mu is actually a critical point of what I call the action functional, which is nothing but the Hamiltonian plus mu over 2 squared. Means this prime mu and prime mu equals 0. This is exactly the equation we have. And so L mu is okay, so the spectrum of this is very well known. It's not difficult to check that it has this. So it has entirely purely imaginary discrete eigenvalues on the imaginary axis. Moreover, at least if they equal 1, all these eigenvalues are simple except in the null space here. In the null space, we have actually this relation. This is true for all theta and all mu acceptable mu, right? So if you get the derivative, if you take a derivative in theta or in mu at theta equals 0, what you have is that a mu of mu phi mu minus mu, and a mu of I phi mu or j phi mu. So you have a kind of simple but degenerate eigenvalue at 0. So if you project on this null space here, the deterministic equation, what you get is something like a two-dimensional system which has a form like this, right?
So multiplicity of 0 is 3 or 2.
This is a generalized eigenvalue. Multiplicity 2.
And just you haven't said, but it seems almost clear that L mu is self-adjoint. L mu is skew self-adjoint.
No, L mu is self-adjoint.
Yes, L mu is self-adjoint. Yes.
But G L mu is not skew adjoint because J and L mu do not commute.
So J L mu is not skew self-adjoint, but still have eigenvalues this way.
Yes. Okay, so you see that now if I had a noise, linearize the equation, and project on the null space, what I should get is my results, so I have to get it first, but I want to explain the results. Now, as noise, like this one, linearize and project on the null space. What you will get is some system more or less like dx. So dx1 will be minus x2 dt plus epsilon dw1. No epsilon. Well, I have to be a little bit more precise here because I linearize. I suppose I have a solution which starts from exactly I mu. Okay, then in this case, the remaining term in the solution will be of order epsilon, right? At least up to some time. So when I linearize this, I take the first order in epsilon and I get this kind of thing. So there is no more epsilon here. Well, here, W1 and W2 are correlated Brownian motions, but they stand for the projection of the noise which becomes additive because I have a linear line on the null space. So you see, here what can you expect? So it means that you have like one of t, which is more or less already two of them. Yes, already one of t. You start from 1 is 0 and 0. Right? So if you only consider this term, which should be the dominant one, well, you cannot expect more. This is just formal. I mean, I don't know how to prove such an estimate, but this is natural. And the probability that epsilon x1 of t be larger than some constant delta, which is, you want to know where you leave the domain of the linearization. Right? This will be less than some exponential of the constant divided by epsilon square t3, because this is equals. Right? So what we wanted to do is use the fact that actually the deterministic solution is stable, is orbitally stable, to get better estimate than that. Means that, what does it mean? I have my orbit. So this is phi mu. This is the orbit e to the I theta phi mu. Stable means that if I start, for the deterministic equation, if I start sufficiently, so I have a kind of neighborhood of this orbit, and if I start sufficiently close to the orbit, then I will stay in this neighborhood. And so the proof of this was done by Veronica Cudini and in 2003. It's a little bit different than that about the Harmonic potential, but still, what you are doing to prove that is you use, in some sense, this S mu function as a Lyapunov function, because it is it is conserved along the solutions of the deterministic equation because both the Hamiltonian and non-dilated are, right? So it's constant. So the fact that it's constant gives some estimates. Why? It's because you have this relation for some positive mu. Not always, of course, but under the condition that V is both orthogonal to phi mu and to I phi mu. So it's not completely obvious that, of course, if this was always true, it would be rather easy to prove the stability because the conservation, you just perform a Taylor expansion of the S mu of your solution. Use the fact that it's conserved, so it would be the same value as at time 0. And use the fact that this term here, so S prime of mu of phi mu is 0 because phi mu is a critical point. And the second term provides an estimate on the remaining part. Okay, this is not always the case, but you can choose your parameter theta because what you want is orbital stability in such a way that you are orthogonal to one of these two functions, then the conservation of epsilon gives you, in some sense, the Hasbro orthogonality condition. More details on that, but then what is our result? So, sorry to be late. So, the result is the following. Suppose the solution of our equation, which is no more on the board, but it's the total nonlinear equation with noise. It starts from psi naught equal phi nu. Not exactly from a standing wave solution of the differential. Then there are random parameters. Type epsilon of t and mu epsilon of t, such that you may write the solution as e to the theta epsilon of t times phi mu epsilon of t plus some limiter, which, as I expect, is order 1, so I write it like this. And so what we impose on this parameter is that eta epsilon will be orthogonal to phi mu and to phi phi. And this holds for t less than some stopping time, which depends on the constant delta. Delta should be a sufficiently small constant. And we have estimate on this stopping time. Actually, we can define it in fact. So epsilon delta is the first time for which we have either the remaining term which becomes too large, or the parameter mu which becomes too. So I should have put a mu 0 here. Mu 0 is fixed. So here I have also mu 0. And we have estimate on the stopping time. The probability that this is less than t will be bounded by a constant. So this depends on delta. So this is a better estimate than the formal one we had. Just projecting on the space. And we can, well actually I think I have to stop now, as you want.
How much time do you think you will need more?
To write and explain the complete result maybe 5 to if you were already to.
Maybe you can finish with the result and exactly.
Yes, but then it's not so, I mean, to state it, and I have to explain a few things. So actually, mu epsilon and theta epsilon are semi-martingale. So they satisfy the stochastic differential equations, but as I wrote the decomposition here, these equations are coupled, of course, to the equation for the remaining term eta epsilon at order 1. This is due to the fact that when I explain this argument here, I say I project. So what does it mean I project? Actually, it means that I use spectral projection. And if I denote by P, say mu 0, the spectral projection on the null space of L mu 0, this orthogonality condition do not say that P mu 0 of, this is a remark, these orthogonality conditions. So of course, why did we choose these orthogonality conditions? We choose them in order to be able to use the stability argument to get our estimates. So these were convenient to get our estimate on the stochastic time here. Right? But they do not imply that P mu 0 eta epsilon is 0. Okay? So due to this, I have a coupling between eta epsilon and boost parameter theta epsilon and mu epsilon at order 1. But I can actually afterwards I can change a little bit my parameters to get new parameters which satisfies this mu in some sense orthogonality conditions, and for which I have the same estimate on the same time. So afterwards but I have to change a little bit my parameters. So in this case I get an equation which is of the form D. So at order 1, so mu epsilon is small o of epsilon and theta epsilon will be. So there is another one term here, which I minus epsilon projection. This term comes from the projection of the nerve section. So what does it say? So this one. So what does it say? It said that the noise will not act on the frequency mainly, but on the phase. And then we also have that. Okay, I can't write everything, but it's quite technical because.
Maybe then, if in that
I can just say what we obtain. Then what we do is we obtain what I call, but maybe it's an improper term. The central limit theorem, which I mean by that is just that we justify in some sense the linearization. So eta epsilon will converge. Eta epsilon converges to a Gaussian process, which is just the solution of the linearization. Natural, but it's natural, but technical. And then we study the behavior of eta as the frequency goes to its minimal value, which is given by minus dimension. So this is only for d=1 because we really need a special structure that the spectrum has. In particular, as d goes to -1 in dimension 1, as mu goes to -1 in dimension 1, the phi nu rescaled goes to the first eigenfunction of the operator minus the fantasy square differential. So it's and all the other eigenvalue are well known. It's just the eigenfunction. So you can use this well-known structure to be able to study the asymptotic as mu goes to -1 in dimension 1, and we can prove that actually the what is sometimes called the expected mod powers, that is the mode of this process theta, which corresponds to the case eigenfunctions, kth eigenfunction, in some sense, concentrates on the second one. But it's rather technical to write completely.
We can maybe read later. Is it finished, this work?
Yes, this work is finished, and the paper is going to appear. It's in asymptotic analysis. So I don't know if it's the end of 2009 or the beginning of 2000.
I think that's good if somebody is interested to go to read the paper.
Put a preprint on the web or
I have a preprint on my webpage, or maybe not on my webpage.
But you can send.
But in my, I mean, from my webpage you can go to the preprints of my department. But if you wish, just I have reprint somewhere I can send you. I have the PDF file. So I can find out.
Finished?
Well, yes, I think so.
Yeah.
So
So
it's
thank you very much for this very exciting talk. And we still